You're saying here that it's used for sample matrices, okay, to get to some matrix interferences. So you see here, you can have different amounts of standard is used. You can use 5 milliliters and then add it to your sample continuously. What that means is the absorbance increases continuously, right? Initially, if your sample has an interferent, before you add it at 0 absorbance, it still has some absorbance due to your matrix, whatever component. Yes, it may have lead in it.
So the standard that's being added, is that just what you think that what the interference might be? Or
is your analyte. So the way it works is, if you have, for example, there might be some lead in the sample itself. So lead itself is not at 0, you know, it is already there. So by the time you try to have a blank to 0 it, it still has an absorbance due to the lead in it. Okay, so that is everything else other than the analyte absorbs. I see what you're saying, that you think this matrix itself gives a signal and you don't want.
So then what would the spiking process be for this sample with lead in it?
So normally the matrices are going to react with your analyte itself. So in other words, even if you have this is a soil sample, all right? This is a blood sample. So normally you prepare standards, right? You prepare standards and say this is 0 and so forth. Then you give a blank, okay? But instead of that soil sample itself, it is going to give an absorbance due to whatever the matrix has, lead itself. Let's say here, the different, let me say here, this is normally what happens is the absorbances are not very linear, or they will be lower because of the matrix interacting with your analyte. So there is lead, but the here is what I'm using the example of lead, okay? Within your sample itself, there is lead, but that lead that is there interacts with the matrix itself, okay? So you do not get a true absorbance. To counteract that, what you do is you add standards whose concentration you know, and you would assume it's not going to interact with whatever matrix. You got it? So usually that's how the matrix interferes with your analyte, because it gives you another reading, but that reading may be lowered. So you spike it to get a reading from. So you get 2 readings. You get a reading from the spike and a reading from the matrix. Okay, if there is 5 ppm of lead, then you get the reading from the 5 ppm of lead before you add anything at 0. And then when you spike it, all right, you spike it here. So what you get is this reading here after spiking it with a certain, yes, you see that? That's the concentration, grams per milliliter or molar concentration, whatever the concentration. You spike it with that one, and then you get a reading plus whatever it was reading. And then you get another 5 milliliters, what I use. Then 10 milliliter, the concentration has increased. And then that also would give you from 10 milliliters plus what was that. So then you can, that is linear. That is a linear response. Make sense there?
Yes.
So normally you can suspect this when you get very low concentrations of your analyte. Low concentration, unexpected low concentrations. Then you can start to say, well, maybe I have matrix interference. It is reacting with my analyte.
So what if you have something like, say, with fluorescence, where it works better when it is at really low concentration?
Where would you,
Would you use standard addition in that situation?
yeah, you can also use standard addition actually. But often standard addition is used for AA. Standard addition is not limited to AA. It can be used for any analytical method. Okay. So I thought this is something that we need to be sure about. Okay. So then we go here on what I planned for this afternoon. Atomic emission spectroscopy. You see in chapter 10, and the problems here, number 1, 2, 6, 8, 9, and 10. Okay. So in, okay there, yes,
What
ma'am.
are the chapter 9 questions?
I didn't want to bring it at this point. Maybe a Friday will be a better time. Friday would be better. Friday would be a better time so that you can go through. Okay. So you notice there, those are the problems there. Those are chosen. I've chosen them carefully so that they drill you into what ICP is all about, or atomic emission specifically. ICP. So in atomic emission, remember it's emission. So in atomic emission, it's based, we have what is atomic emission. We want to answer that. Emission spectroscopy that is based on plasma sources. That's what is atomic emission. Atomic emission that's based on plasma sources. When I talk about plasma, I just have to remember whoever asked, what is a plasma? Remember who that was? As a teacher, I remember. It is Miss Taylor. Oh, you forget the question you asked me.
So, I forgot what I ate yesterday. I'm not even gonna lie to you.
She asked me what a plasma is. And I answered, it's a mixture of cations and electrons, right? And I also said argon, cations and electrons. I think she's forgotten. That's a plasma. So emission spectroscopy based on plasma sources. We'll define our plasma. I've already defined it, but we'll define it. And so these are some of the techniques that we use for atomic emission: inductively coupled plasma, direct current plasma, the plasma source spectrometer, and then we'll talk about some of the applications of plasma sources. So there is also emission spectroscopy, which is based on the arc and the spark sources. I won't go into those details. This was very common, 70s, 80s. Some labs still carry those. But if you happen to be in such a lab, I will mention them for completeness, okay? But if you happen to go in such a lab, or later on, when I grow up, I become bigger, then you happen to supervise other people, or you become a scientist who advocates for science, then we want that as well. We want everybody, okay? So this is largely limited to the elemental analysis of solid samples, and we are not going to cover that in our class, okay? So let's move on to atomic emission. Remember, you know atomic emission. This diagram here emphasizes what atomic emission is. First, notice you can excite atoms. This is excitation from the ground state. This is for sodium, the 3s orbital. You can excite them from the 3s to the 3p, or 3s to 4p, 3s to 5p, and so on. And so this is, you can excite them using thermal energy or electrical energy, all right? So simply excite the atoms. It's atomic emission. Then they go to all these other orbitals of a higher energy level. And if they come down from the higher energy levels to the lower energy level, that's what we call atomic emission. So you are measuring the energy associated with atoms from the excited states coming down to the ground state. Yes, sir.
I just wanted to get a quick recap. And fluorescence would be when it stops by each of the vibrational states on its way down.
For fluorescence, we can have atomic fluorescence, we can have molecular fluorescence. So in atomic fluorescence, it can go from the excited states to the ground state, very similar.
It can go just straight to.
Yes. It's very similar. It's an emission, actually. The only difference is in fluorescence, they have to go from a singlet state to a singlet state. It's very specific. So that is the specificity for fluorescence. The orbitals have to have the same orientation, same shape, right, for that to occur. So the rapid relaxation of the excited states is accompanied by emitting UV light and visible light at discrete wavelengths. So you can see here the wavelengths for this sodium line. You can see we have various lines here from 5P to the 3S, the 285 nanometer line. You have from 4P to the 3S, 330 nanometer line. Or the commonly used line, it's 589. You can see here 589, although it's at 590, it's actually 589. It's 589 nanometer line is commonly used. And this is in the UV light, the UV region, and the visible region. So that's what you see here. So the excitation source, as we have said, the stimulus, is to promote the chemical species up to the excited states. You can do that thermally or electrically. So you can do that. It can be by a plasma, or it can be by a flame. It can be by an electric spark or an electric arc, thermal or electrical. And in atomic emission, we measure the emission of light from atoms. That's what we are measuring, atoms. And the intensity is proportional to the concentration of atoms in the particular excited state. We're talking about intensity is proportional to the concentration. You can see here, this is energy, EV. That's the associated energy that you need to effect that excitation and then the emission, right? Any question here? Everybody is okay here? Okay. So here then, the basic components of an atomic emission spectrometer. Look at the basic components. Is there anything that you identify with here? We now know all the instruments, most of the instruments. They work on the same principle. So you have here wavelength selector. Number two, you have a source. You can see here, one of you asked me, is it like a fire, right? What did I answer? It is yes, but it's not a flame. Actually, it looks like a flame when you light it, but it's really a bloom of these ions and cations at very high temperatures. But it looks like a flame. It's a torch. It's a torch.
Is the plasma?
Yes, that's what that is actually. That's the plasma you see. It looks like a torch when we light it. And so that's what you have here. So you can see here two things that you may want to see. You have a sample. You have a sample here, and you have the torch. Did we see this upstairs? You have the sample. Then you have the nebulizer. After that nebulizer, there is something covered, which I did not open. That's where the torch is. We're together there. So it's the same kind of thing there. So you see you have the sample in the either the vials or whatever sample holder, tubes, and then it is aspirated into the nebulizer, then it goes to the torch. And this torch here, notice it's at 90 degrees. The radiation source and the detector are in 90-degree direction. So you have an emission here as the atoms go back to the ground state, as you can see, then you choose the wavelength. So each element will have its own wavelength. Now you might remember what I say. The advantage of using emission spectroscopy is what? What's the advantage over AA?
Is it higher sensitivity, selectivity?
Yes, there are many. That's one. High sensitivity. You can. Yes, Josh. You can analyze multiple elements at the same time. I'll show you how. The detector actually has like what we talked about at the end of it, like a PMT, okay, but not a PMT. Before we talked about the PMT, it has photo what? What did we talk about last time? It has photodiodes on it. Yes, because before we talked about the PMT, we talked about photodiodes. So it turns, and so every light will go to one diode. All right. If it's a diode, that is, if it is optical, are we together there? If it's optical, if it's a mass spec, every ion will be detected with its mass.
Doesn't PMT use photodiodes?
Yes, a PMT is many diodes. It uses diodes to amplify the signal, but it's based on the same principle of diodes, actually. But diodes, remember, usually you have a series of them. Each is specific for a particular wavelength.
So is the detector the photodiode?
It can be a photodiode. It can be, what's the detector? The detector can be a mass spec. A mass spec is the detector. Or, remember the detector in UV, what was the detector? Can be a PMT, all right? For a mass spec, you are going for the charged ion, okay? For the diodes, you are going for the wavelength. So yes, you can have either, depending on what that detector is. Mass spec is very common, or you can have the diodes. All right, you notice the radiation source and the detector are in 90-degree direction, and that is important. So the stimulus for atomic emission is a plasma. So a plasma, what was the question again? Ms. Taylor. Okay, a plasma is an electrical conducting gaseous mixture containing a significant concentration of what? Cations and anions. They are actually of equal proportions. You'll see how that works. Usually you have the argon. So it contains cations and what? And electrons. Cations positively charged, electrons negatively charged. The concentration of the two are such that the net charge approaches zero normally. And argon gas is one of the most widely used plasma species. So you would excite the plasma. Why do we use argon? You can think, normally we know this knowledge. Why?
Light, very stable.
It's inert. Yes, it's inert, so it doesn't react with, although it forms other species though, but relatively it's inert. We use it for that case, but it will react and form other species we'll see later, okay? Like oxides, ARO, and OH, and so forth. That's one of the problems with this. So argon gas is one of the most widely used plasma species, and it provides a temperature as high as 10,000 K, that's around 5,500 degrees degrees Celsius. There are three types of plasma considered for atomic emission. One is the common one, the inductively coupled plasma, ICP. The other one is the direct current plasma. The other one is the microwave induced plasma. Most of them have the term or the word plasma. So inductively coupled plasma happens to generate a higher temperature than the direct current plasma. Okay. Sometimes we need to see these to make an impact. Okay. Right now, I'm just talking about it theoretically. Okay. So here, this slide is very, very important. This particular slide is very important. Let's, I'll give you time to write it. Okay. What are the advantages of the emission spectrometry over absorption, either AA? What are the advantages? Number one, it has lower inter-element interference because of a higher temperature. Lower inter-element interference. Remember we talked about spectral interferences in AA. So spectral interferences are there, but they are lower inter-element interferences because of a higher temperature. Number two, the emission spectra are obtained under a single set of excitation conditions, and several elements can be recorded simultaneously. The one upstairs, I have analyzed up to 30 elements, just one time. For just one element?
For like the 30 years.
For 30 elements, it can take not too long. It's not very long. It's in a matter of a second or a minute to 3 minutes. There are stages, but that's long. That is short enough. Yeah, it's very, very short. So emission spectra are obtained under a single set of excitation conditions. And you can analyze several, the advantage here is several elements can be recorded simultaneously. So unless you have many samples, for example, Haley, when I have about samples, if I have, let me see how many. If I have 60 samples, then it can take 2 hours, which means 3 minutes per element. Something on that range. But 3 minutes should be. So multi-elements can be analyzed from very small samples. Remember, if it's absorption methods, you have a large amount of samples. Number 4, there is a low concentration of refractory compounds that can be determined. You remember what refractory compounds are? Can you give me an example of a refractory compound? We talked about it in the morning. We understand what refractory means? Huh? No, that is, no. Refractory means you can't separate them very easily. That's what refractory means.
Can't separate it very easily.
They are hard to separate. Yes, usually that's what refractory means. Something which is a little bit difficult. If you have a refractory person, that's, imagine. For example, what we talked about in the morning is calcium oxide, okay, or aluminum oxide. That's refractory. So there are low concentration refractory compounds because you heat them up at very high temperatures and you separate them. So you can see those advantages. You can see another advantage. Non-metals can be determined by plasma sources. You see that? We can analyze both metals and what? And non-metals at the same time. As long as you set your wavelengths, if you are dealing with optical ICP optical emission spectroscopy, or if you're dealing with mass, ICP mass, you set the masses of the elements. If it's zinc, 29 or 30. If it's copper, you set 63, then you can analyze those. So you can analyze. Now, the other thing is you have a very high dynamic range. For plasma sources, you have a very high dynamic range. Those are many. If I ask 3, I expect people to give me 3. Okay? Don't forget, this is what I ask in an exam. Okay? So then, did you all get that? I want to showcase you something we did. This is over many years ago. We were analyzing foods. I gave you that story. And you see here, this is, I went to the store, I said, oh, I eat these peanuts. I wonder how many, what's the concentration there? I just buy it from the store, bring it to the lab. Say, okay, I have oranges, but we eat orange peels and we also eat the flesh. I wonder how much of these elements are there. That's curiosity, right? That's me. It may be known, but I wanted to see what is there. I wonder if the bananas that I eat, banana peel, and say, why we normally peel them and throw them away. I wonder if these are useful, right? Then we mash them, and then mash it, what do you call it? We cut it down with, what do you cut that with? Huh? What?
A knife?
Yeah, you cut it with a knife, or there is a machine you put them, like a blender.
Oh, like a food processor?
Yes. Then I have one in the lab. So we cut them and then chops them in small pieces, then we digest them to put them into solution. And so on. So you can see all those kinds of things. And notice here, this is ICP-OES, optical emission spectroscopy in the soils lab. Okay. So we did that. You can see the date is even there. I was looking at this data and say, wow, I did this many years ago. 2012. Yes. So that was March, and I continued doing this, and up to some time other students came and did this work. So this is only a sample. I only took a sample. This table is the same. It's reported as percentage, or converted to ppm. By converting a percent to ppm, you multiply by 10,000. So now I'll showcase that to show you how many elements we were analyzing. These are not all. I only took a sample here. You can see there, potassium, phosphorus, calcium, magnesium, sulfur. You can see, just select the wavelength for sulfur. Whereas in AA, if you're going to analyze sulfur, what do you need to do? What needs to happen to your, the setup in order for you to analyze sulfur?
Wouldn't you need like a sulfur? You would need to analyze the sulfur.
Under what wavelength conditions would you analyze this? No, it's right here. It's looking at you here. That's angstrom.
Oh.
Divide by 10. 182. Compare these other ones, 286, 315, 766. Those are in the visible UV light. This is in the, these are in the visible region for sulfur and phosphorus. Those are in the vacuum. So for those non-metals, you have to create a vacuum. And you can do that with the kind of instrument that they have. Does that make sense there? So for AA, if you have to analyze these metals, these non-metals, you have to operate in a vacuum, which is sometimes difficult to do. So we have talked about the plasma, and I will not repeat myself there. The plasma contains significant concentrations. In the argon plasma is frequently employed for emission analysis, and the argon ions and electrons are the principal conducting species. That's what the plasma is. Although cations from the sample will also be present, but two of them that are important is the argon cations and the electrons. That's what normally we analyze. So now argon ions, I'm shortly about to stop here, then I'll pick it up. Argon ions, once formed in a plasma, the argon ions will be formed in the plasma. You know what the plasma is? You form cations and what? Electrons. So that forms the plasma. We call it an argon plasma because you use argon to generate cations, and then it gives the electrons. So once formed in a plasma, it can absorb sufficient power. Maybe I need to explain myself here. I want to explain myself using a diagram. So I've gone ahead. So this is the diagram. You notice here, what we saw is there is argon. So when we went in there, I pointed you to the argon tanks, right? And then they are connected to the instrument. So those are the argon plasma support flow. And there is a sample. You see, there is a sample there. See, there's a sample, aerosol, and the nebulizer. And then that is typically, after that, there are three concentric quartz. And you can see there are three concentric quartz tubes. And usually they withstand these very high temperatures before then you go to the torch. The torch is really what you see as those conducting electrons and argon. All right, I see people have switched off. I switch off myself. Right. So we pick it up here on Wednesday in class. And then we'll continue. I would explain this diagram so that everybody understands what happens in that class.
And then on Wednesday, are you gonna be in your office
And
Wednesday?
yes,
See you office, okay,
yes, I'm always there.
okay.
Have a good day, sir.
Thank you. Make sure you turn in your lab reports. Turn them in, please.